So this is our problem statement, and we're going to begin by identifying the given and find. So given we have acceleration in the x is negative 4.905, velocity in the x is 5, time is 15 seconds, and then these two are 0 because it's not moving up or down, it's on a flat surface. And we need to find velocity final and displacement in the x direction. So here we see the object is moving on a flat surface, and this is probably where the object ceases to move, so it's called the velocity final. And then this is the displacement of the object, which is delta x. So here are our equations. These are the three equations that you must know in order to solve any free fall projectiles problems in physics. And we have color-coded the givens as orange and the blue as find, and we notice that in this problem it's an ideal situation because the givens for these two equations are on one side and the finds are on one side, so we don't have to worry about manipulating anything. So the algebra really consists of figuring out which equation is best for solving which problem. So we decided that this is best to use to find velocity final because we're solving for that in this problem. And we only have given and finds, no unnecessary information. And same with this one, it has displacement, that's what we're solving for, and it only has the given and finds and no unnecessary or unknown values. Velocity final in the x at 15 seconds, which is after the 5 to 10 second interval. If I plug 5 plus negative 4.905 times 15, which is our given time, we get negative 68.575 meters per second, and velocity can be a negative value because it kind of shows whether the object is moving or slowing down or speeding up. And then to find delta x over the 5 to 10 second interval, I essentially began by plugging in the time value from 5 to 10 seconds. So here I have 5 here, and 5 here, 6 here, and 6 here. So these are the only values that I changed from the 5 to 10 second interval. And then I added all of the delta x from the 5 to 10 second interval to get negative 224.17.528 meters over the 5 to 10 second interval as the displacement. This is a velocity time graph, which I essentially used this process, and instead of putting 15, I put 5, 10, 16, so on and so forth. Position time, I did the same thing over here. I used most of the points from this set of values, but I also went to 11, 12, and the only thing again I changed was this value over here and this value. And now we move on to problem number 2, which basically says Olivia jumps from a low cliff at an angle of 50 degrees above the horizontal with a speed of 2.5 meters per second. Delta y is 6.5 meters. Calculate the following, and we have like 7 things to calculate. So identify, we have velocity initial, theta, we have y at 6.5, acceleration in the x is 0 because it's not directly moving left or right. Acceleration in the y is negative 9.81 because it's moving down. Olivia is moving down from the cliff, she's falling down. And velocity max is 0 because in a free fall or projectile, the max velocity is always 0. The velocity at a max height is 0, and we need to find velocity initial in the x, velocity initial in the y, the time of flight, time max, height max. It's supposed to be a delta value here, velocity final, and also delta x, which is the displacement in the x direction. Here I have my diagram. So there's 2 because we want to show the displacement in the x, displacement in the y, or the range of projectile. And then here I have my delta y max value, and I also created a triangular, like a trig version of it, so I can solve or use it to create a few equations in my algebra step and my equation step. And yes, that's that. So the equations we have are right here. Number one is this equation right here. Again, the givens are in pen ink and finds are in pencil. 2 is right here, similar to, and basically I found these two equations by looking at my triangle here and trying to solve for these values. Um, this is actually, so this is number one, excuse me, not this one. This problem is number one. This is what we use to solve the problem. This is number two, number three, number four, number five, and number six. Again, these are all problems that, number six and number seven, excuse me. These are all problems that we should know and we need to know in order to solve our equations. And for free fall and projectile, it's always useful to create these at an angled launch to create these triangles so that we have velocity initial and velocity initial in the x to solve for. And yeah, that is the equation step. The algebra step is a little bit longer for this one. So for number one and two, as I stated, I found this equation. So I really only need to plug in velocity initial and cosine theta, velocity initial sine theta, and find my answer in the solve step. But for number three, I'm going to be using this equation right here, and I already know what my delta y value is, what my velocity initial and sine theta is, but I don't know what my time is. So in order to get time alone, I'm going to divide by velocity and sine theta to get this equation right here, and I can solve from time from that equation. And then number four is this equation right here, velocity max y. So again, that's just a variation of this equation right here. However, I'm trying to focus on one specific velocity at a certain time and things like that. So for what I did was that I needed to get T max by itself. So I subtracted velocity initial times sine theta, and I got velocity max y minus velocity initial sine theta, and I needed to divide by acceleration in the y. So that's what I did there to get this value. And then number five, I used this general equation and I focused on a specific y value, and I manipulated this and wrote it in a different way that basically meant the same thing. And then of course with time I also changed that. So I only changed like a few things about the general equation to create this equation right here. Number six, given our finds are all solved for in these prior equations or are given, so we just need to plug it in. For number seven, velocity final is equal to the square root of velocity x, and then I added velocity initial in the y plus 2ay delta y, and then I square rooted that in order to get this. And lastly, I solved for each step. I plugged in the values to get each value that was necessary for this problem. Again, it's only about like changing the general equation. Like I